So getting a few questions in my inbox about how does a charging blanket actually work and what are we doing? Thought I'd spend a few minutes today just going over that because it's actually a pretty cool product. Whether we're talking an air conditioner or we're talking a heat pump, both of them have to be charged in the cooling mode, right? You cannot charge the heat pump in the heating mode. You can only get it within reason, but you cannot dial in the charge exactly. If you're putting in a heat pump, you're going to have to return if you don't get the charge done. Same thing with an air conditioner. If you don't get the charge done, when the conditions are less than optimal. And less than optimal is typically, depending on the manufacturer, anywhere below 65. Some will go as low as 55 degrees, but typically around 65 degrees, we start falling off, and it's just not a good idea to test charge typically using traditional methods. Let's talk about, first of all, why is that? And we'll do a little review here of the basic refrigeration cycle, right? A lot of people, when they talk about the compressor, they always say it creates a pressure difference. And yeah, it does create a pressure difference, but its job is to actually create a temperature difference, right? Because we're absorbing heat from a place where we don't want it in the house, rejecting the heat outdoors where it doesn't matter. And the compressor is what's creating that temperature difference that allows us to reject that heat outside. Obviously, the condenser has to be hotter than the outdoor air and the evaporator colder than the return air, but it's a balance here. And so when we're doing this, a lot of times I like to just divide this up here and say, okay, well, this is the low side of the system, and this is the high side of the system. And what we're trying to do is maintain enough of a differential pressure across there so that we get the right rate of heat transfer due to the temperature differences. And obviously, that also helps with refrigerant flow, right? So there's a couple of things going on here we need to make sure we understand. First of all, is that we want to have a liquid seal at the bottom of the condenser. So the whole idea here is that we only supply liquid to that metering device. And to do that, we typically want somewhere around, we'll do it on this side just so we have room over here for the charging blanket. But to do it on this side, we typically have about 7 to 10 degrees of subcooling. And that means that we're just below the saturation temperature, 7 to 10 degrees below the saturation temperature. And that provides a liquid seal. So we know if we're below the saturation temperature, we'll make the C a little bit bigger. We know if we're below the saturation temperature, we have 100% liquid here that's going into that metering device. And a metering device can only meter liquid because obviously if it gets a mixture of liquid and vapor, it's not going to respond properly. Once it goes to the metering device, we're creating a pressure and a temperature drop, and we're filling this evaporator almost all the way full with saturated liquid. And that's saturated liquid. When we measure our superheat, we're typically anywhere from around 10 to 12 degrees of superheat, right? That assures this evaporator coil is about 90% full, right? So we're 90% full. We have a fully active evaporator. We have a liquid seal in our condenser, and that's what we want to have. Now, what's cool with this is the metering device. If we were to draw these couple other lines here, there's one line that goes up here, and it measures pressure, right? So this is P. We'll put a pressure on that. Another line that comes up here alongside of it, and it measures temperature at the outlet of the evaporator. So we're measuring a pressure. External equalizer line measures the pressure. The bulb measures the temperature, and we're maintaining that the spring pressure is set here, let's say for 12 degrees of superheat, and that valve's going to maintain that 12 degrees of superheat all the time. Now, this is what makes this really important, is that when we have 12 degrees of superheat, the level in the refrigerant in the evaporator does not change, and therefore also the level in the condenser does not change. If we're on a 75-degree day, or a 95-degree day, or a 110-degree day, the level of refrigerant in the condenser does not change. It stays about the same. Now, the condensing temperature will go up. The liquid line temperature will go up. The superheat and the subcooling, though, will stay the same, right? Because when we have an increase in condensing temp, if we also have an increase in liquid line temp, then we'll see that basically stay the same. So if we're talking about this, let's throw some numbers in here. So let's say that we have about 118 pounds of pressure on our low side. So that means we have about a 40-degree evaporator coil. And let's say that we have around, let's say 390 pounds on our high side, right? And that would be equivalent to around a 95-degree day, or about a 115, let's see here, a 115-degree condenser coil. So we had 95-degree day. So this would be basically, if we go over here, we have 75-degree return air, right? So the evaporator is 35 degrees colder. 75 minus 40 is 35 degrees. It's called our DTD. And our condenser over here, we're at a 95 degree day. So we take 115 minus 95, and we're at 20 degrees CTOA. So condensing is 20 degrees over the ambient temperature, right? And those are our condensing temp over ambient and our design temperature difference. But to get the idea here is that there's a large differential pressure here. So if we were to take this 390 minus 118, 390 minus 118, we're somewhere around 272 pounds differential pressure across the metering device. So here's where it gets really interesting. In order for this metering device to work, if we're talking R410A, or we're talking 454B or R32, we require about 160 pounds of differential pressure across the metering device for it to work right. We're talking R22, right? Then we're talking about 100 pounds difference across the metering device. It's all about differential pressure. This metering device can only open up so far, and it can only open up so far, so we have to provide it with enough differential pressure so it can fully feed. It can be higher than 160, but if we're lower than 160, what happens is liquid starts to back up in the condenser because there's not enough pressure to push it out. We starve the evaporator, we flood the condenser, the refrigerant does what we call migration, so it ends up sticking in one spot versus the other. And then the valve, when it senses that the refrigerant does get too much, it usually does what we call hunting. It just can't control well. So that higher differential pressure, 160 pounds or above, or in this case, in this example, 272 pounds, makes a huge difference on how that metering device performs. So the idea here is that we want to maintain that differential pressure. In this case here, we're talking about having a 115-pound condenser here, but what happens if we're to change this? And let me see if I got an eraser here. Let's grab a rag here. And we're to change these pressures and temperatures a little bit. So we'll keep the indoor, we'll just keep it at 75 degrees and 40 degrees. We'll get rid of this 115-degree condensing temp. And let's say that we have 50 degrees outdoor air. So if we have 50-degree outdoor air, 50 degrees, we'll keep our CTOA the same, plus 20. That means we'd have a 70-degree condensing temperature, right? So 70 degrees, because we have 50-degree air going across this. This is our ODA, outdoor air, plus this is our CTOA, and this is our condensing temp, right? So we have a 70-degree condensing temp, but a 70-degree condensing temperature now, we're at about 200 pounds across here. And if we're at 200 pounds and 118, our differential pressure, so we took 200 minus 118, that equals 82 pounds differential pressure. Is about half what that metering device actually needs. So now here's where the charging blank comes into play. So we got our condenser fan here. We put a blanket over top of this and create an orifice here. And what's going to happen is some of this air from this condenser is actually going to circulate back inside the condenser, and it's going to raise this condensing temperature up. So even though it's 50 degrees outside, we can get this back up to let's say, equivalent of 115-degree condensing temp again, or a 90-degree day. So we can take that pressure all the way back up to 390 pounds, and we can then feed that refrigerant to that metering device at the right rate, right? And so it's just a matter of, again, recirculating the condenser air, raising the pressure in the high side of the system by increasing the temperature of the outlet of the condenser, and basically it allows us on our 50-degree day to take that back up and adjust it. Now, in the application, what we've done is we're looking at, in real time, always watching our evaporator. So we're always watching our low side, we're always watching our high side, and we're maintaining an optimal differential pressure across the metering device at a range, I think, from like 160 to 220 pounds across the metering device. You don't have to crank the charging blanket way down, but you do have to dial it back a little bit, and that's going to raise your pressure and temperature. And this works great till about 35 degrees. Once we get down below 35, you simply don't have enough heat in the air to create the differential pressure needed to fully feed the metering device. But the idea here, what you want to understand, is that all we're doing is raising the pressure and temperature of the condenser to create the differential pressure to properly feed the metering device so we can maintain a correct level in the evaporator. Once the metering device can control, it can now start to throttle back because it's got enough differential pressure behind it to get the evaporator coil level right, which allows us to get the condenser coil right, which allows us to dial in the subcooling to the exact charge we need. All right, so now let's talk a little bit about a fixed orifice metering device. So we'll just say fixed here. And a fixed orifice metering device is a little bit different than a TXV in the fact that the superheat now, instead of being held constant, like the TXV maintains a 10 to 12 degree target superheat or constant superheat, with a fixed orifice metering device, its superheat is based upon the differential pressure. So we have to look at what's the delta T or delta pressure between the evaporator and the condenser to get the target superheat. We need an evaporator. So let's just talk about that for just a minute here. So if we were at a 118 pound condenser, and that again is about a 40-degree evaporator coil, right? And it was a 95-degree day. So again, we got to look at what's our 95-degree day, 95 degrees ODA, plus a 20-degree CTOA. It's our condensing temp over ambient. So that's on a 13-SEER condenser. How much hotter is our condenser than our outdoor air? So 95 and 20, that's 115-degree condenser. So this is 115 degrees, right? And a 115-degree condenser, we're at about 390 pounds across that, 390, not degrees, but pounds of pressure, right? So we have 390, 118, so we take 390 minus 118, and 390 minus 118 is about 272 pounds differential pressure. So you can see if we required, again, for a fixed orifice, let's say 160 pounds of differential pressure, in this case, let's just take it at actually what it is, at 272, it's 272 pounds of differential pressure. That would probably give us a superheat of about 10 degrees, right? If we had a 75-degree return air temp at, let's say, a 63-degree wet bulb temperature at 95 degrees outdoor airs, right? And I'm just guessing here, if I'm thinking about a superheat, a target subcooling somewhere around 10 degrees, right? And so what that's going to do for us is, obviously, we have enough pressure on the condenser, and you got to remember what's happening here, right? So what we're doing is the condenser is creating a high side pressure. Think of it as just pushing downward on this liquid. We push down on the liquid, we push up on this liquid. So this liquid level is going to go increase. So as this liquid level increases, our superheat goes down. So what we're talking about is the condenser, as it pushes down, subcooling goes down, we have less subcooling and we have less superheat. It just is a balancing act. So if the evaporator temperature were to go up, it would boil faster, the evaporator pressure would drop, condensing temp would back off a little bit, and it would be this balancing act between what's going on inside and outside. And so where this is 10 degrees of superheat, it could be as high as 30 degrees of superheat, which means the evaporator coil would only be this full, right? So we'd be at this level right here, 10 degrees, where we could be as low as 5 degrees, which means it's almost to the top of the evaporator coil in full. So with a fixed orifice metering device, what the challenge is that we have a variable superheat that's driven by two things, our return air wet bulb temperature and our outdoor condensing temperature, right? So that becomes a real challenge. How can we actually determine that? What measureQuick does is in real time is it's watching this return air wet bulb temperature all the time, which is pretty cool because the wet bulb is constantly changing. As soon as you turn on the air conditioning system, the temperature starts to drop, the humidity starts to drop. The temperature and humidity is what drives wet bulb. And when those two change, we need to know dynamically what's going on there, and as well as our outdoor air temperature. So what measureQuick is doing in real time is it's looking at your return air wet bulb temperature, and it's looking at your condensing temperature, and it's determining what target outdoor air do you need to maintain a target superheat on that evaporator coil. So all that we're doing is we're looking at a target superheat, and then we're back calculating what outdoor air temperature would we need to have that target superheat based upon our condensing temp over ambient. So it's very important when you're using a charging blanket that you use a CTOA that is correct for that condenser. So if we're talking a 10 to 12 SEER, we're talking a 30 degrees hotter than outdoor air. Or sorry, 6 to 9 SEER was 30 degrees hotter than outdoor air. 10 to 12 SEER was 25 degrees hotter. When we got to 13 SEER, it got to 20 degrees hotter. And we get to 15, 17 SEER higher, it gets into 15 degrees hotter. But it's always going to be hotter than your outdoor air. So when we profile the system, that's what determines our condensing temp over ambient. And then the software just in real time is calculating what our target head pressure is based upon our return air wet bulb temperature to dial in our exact target for charging with the fixed orifice. So we got this really dialed in now, so you can do either a fixed orifice or a TXV system, typically down to about 35 degrees Fahrenheit. Some larger condensers that may be just too big to allow us to do that, but typically down to about 35 degrees Fahrenheit, and allows us to do both a heat pump or an air conditioner in the cooling mode. And again, we pick up about 2/3 more days to do that. So That gives you a little bit of an idea about how this is all done. It's pretty cool technology. We've really taken something that was obsolete and not being used anymore and made it modern. And with measureQuick, it works with R32, with R454B, with 410A, with R22. So it works with all your low pressure, your high pressure refrigerants, and allows you to dial that charge in any time of year.